Hello students, I'm Mr. Ruffler, a high school chemistry teacher, and welcome to the channel. In this series, we're going to work through the brand new New York State Chemistry Regents exam cluster by cluster. For each cluster, I'll break down every question, explain the chemistry behind it, point out common mistakes students make, and show you how to approach similar questions on future exams. My goal isn't just to help you get the right answer, it's to help you understand why the answer is correct. If you're looking for a different cluster, check out the playlist linked in the description below, where you'll find step-by-step walkthroughs of the rest of the exam. Let's get started. So the first cluster is how glow became gloom. Radium is an element that has the ability to cause certain materials to phosphoresce or glow. When radium decays, it produces particles that excite electrons in some substances. Figure 1 shows the particle production from radium. In the early 1900s, thousands of young women were employed to hand paint numbers on watches. A mixture containing radium was used so that the numbers would glow in the dark. The women dipped their brushes in a powder base containing radium and made the tip of the brush smaller by placing it in their mouths. Over time, many of these women experienced tooth loss and jaw deterioration as calcium in teeth and the bone was displaced by radium. All right, so a lot of information there. Let's take a look at the questions, keeping in mind that we're probably going to have to go back to that passage to answer some of them. So the figure 1 is just showing how radium-226 is becoming radon-222, and it's releasing an alpha particle. What I would tell my students to do is write out these elements in isotopic notation. In order to do that, we're going to need our periodic table. So we're going to look for radium, and we're going to look for radon on the table. Looking at our periodic table, here I see element 88 is radium. And over here on the right, I see that element 86 is radon. So radium has an atomic number of 88. That means that it has 88 protons. And radon has a number of 86. That means that it has 86 protons. So that's going to be helpful information. We can start by writing the symbols and putting the atomic numbers on the bottom. So I'm going to put in the 88 and the 86. And then the number on top, well, that's going to be the mass number. Recall that the mass number is the number of protons plus neutrons. All right, we can put that on the top. So you can say 226 radium will decay into 222 RD, radon. And then we also have the alpha particle. You might remember that the symbol for alpha is just going to be 4,2 alpha. And if you forgot that, you can go to your reference table. And this is under the symbols right here. You could also denote this as 4,2 helium. All right, so for question number 1, it says complete the table below to predict the changes in the composition of the nucleus as the radium atom decays. So it tells us our number of protons, and it tells us our number of neutrons, which if you're unsure, the number of neutrons is just from doing 226 minus 88. So that's how they're getting 138. So we need to figure out the number of protons for radon 222. We already identified that it's going to be 86 protons. And if we do our mass number for radon, which is 222, and we subtract out 86, we'll get that we have 134 neutrons. All right, so for question number 2, it says, use the patterns of outermost electrons to describe how radium could substitute for the element in teeth and bone. All right, so we need to figure out what is the element in teeth and bone. So to do that, we're going to have to go back to our passage and probably highlight. Notice the passage was talking about how the young women would put the radium in their mouths and then they would have teeth decay. And it says they had tooth loss and jaw deterioration as calcium in the teeth and bone was displaced by radium. All right, so that element that we're looking for is calcium. Okay, so let's go back to our table here. So radium is what's replacing calcium. And if we notice, both of them are in group 2. Being that they're both in group 2, they're both going to have 2 valence electrons. So this is the information that we need to know in order to answer this question. So for my answer, I'm going to state that radium and calcium are both group 2 elements, and they both have 2 valence electrons. All right, so moving along, we have a little bit more reading. It says that the Radium Chemical Company, one of the divisions of Standard Chemical Company, marketed a variety of radium products. Figures 2 and 3 show these products. These products have been replaced with less harmful chemical compounds because radium has dangerous health effects. So figure 2 is kind of showing, I don't know if you would call it a propaganda poster, but something vouching for these great effects of radium. And then figure 3 is showing different radium compounds, whether they're combined with bromide, chloride, sulfate, or carbonate anions. So question number 3, it says, which statement identifies the formation of ions in the radium compounds displayed in the advertisement? And then it's saying, how many electrons radium gains or loses, and then what happens to its respective anion. So the first thing that we have to do is identify that in each of these compounds, radium is listed first. And whenever we write an ionic compound, we always write it in the form cation, anion. The cation is always positive and the anion is always negative. So if you're forming a positive ion, that means that you lose electrons. If you're forming a negative one, that means that you gain electrons. So this should be able to help us eliminate 2 of the answer choices. We can eliminate the answer choice that says that radium is gaining electrons. So that would correspond with 2 and 4, because we know that radium is going to lose electrons if it's becoming positive. Okay, then we'll take just one of these, right? So here, if we look at radium bromide, we should be able to identify that each bromide is going to be -1, but then, because we have 2 of them, that's an overall charge of -2. And then that means that if we have only one radium ion, the radium must be +2. Let's kind of check this with the other ones, right? So chlorine here is -1. Each chlorine is going to be -2. So this one's going to have to be +2 as well. And as we go down, radium is still going to be +2. That's going to be -2. That's going to be +2. And that's going to be -2. All right, you could also identify this because radium is a group 2 element. So we're going to pick the answer choice that says radium is going to lose 2 electrons, right? If it's forming a +2 ion, it's losing 2 electrons. And then bromine gains 1 and forms Br-. That checks up as well. Okay, then for question 4, it says that other methods for lighting the watch dial were developed beginning in the 1960s. Figure 4 compares some glow-in-the-dark alternatives. Different energy sources, including electromagnetic radiation, are used to energize electrons in watches. And then it gives us this big figure with all of the alternatives, the nuclear particles produced, the energy source for the glow, and then the glow time. So it says, which statement supports the claim that a watch made with phosphor glows in the dark when electromagnetic energy source is removed? So let's think about the energy source here. It's saying that we have electromagnetic energy source. So electromagnetic energy, in this case, would be visible light. There's nothing that says anything about electromagnetic energy coming from the nucleus of an atom. So, with that being said, we can eliminate choices 3 and 4 because they're talking about the nucleus releasing energy. then the next part of the question, we really have to think about how energy is going in and how it's going out, and then ultimately how that's producing energy that we see in the form of light. So to do this, I've drawn a simple Bohr model of the atom. So let's think about how this is happening, right? It says that the energy for this glow source is light, such as sunlight. So let's just say when we are adding light energy, like let's just say this is our sunlight, we're then going to energize an electron and cause that to jump to a higher state. So this is kind of like that charging period for the watch. And then after it absorbs that energy, we have this model in an excited state. Now, as soon as you remove the energy source, what they're getting at here is that that energy is going to, or that electron is going to return to its lower state, and then it's going to release light energy. And then this is going to be the glow that we see with the watch. All right, so choice 1 says that radiation that was absorbed is released in the form of light as electrons return to a lower energy state. I'm really liking that answer, but let's read the other one. Radiation that was absorbed is released in the form of light as electrons jump to the excited state. That's not what's happening. What we're seeing is an electron returning to a lower state, and then that's when we're releasing that light energy. All right, so the correct answer for this one is choice 1. All right, moving along. It says a manufacturing company wants to design a watch with the following criteria. Criteria 1 is the ability to see the face of the watch in the dark for the maximum time, and criteria 2 is to minimize health impacts. And then it wants you to select the glow-in-the-dark alternative that best meets these criteria by evaluating the information in figure 4. And then you have to justify the selection by citing evidence. Let's just kind of think with that figure what we want to look for. For criteria 1, if we want to see the face of the watch for the max time, we obviously want to look for the max glow time. And if we want to minimize health impacts, we want to pick a non-nuclear alternative. All right, so we want something that's not nuclear and has the most glow time. Let's go back and look at the chart. Right off the bat, we don't want anything nuclear, so we're going to get rid of these two because this one releases beta particles and this one releases beta particles. So then both of these, the superluminova and the phosphor, use light as an energy source. But if we look at the glow time, the superluminova has up to 15 hours of charge. So I'm thinking that I want to make my argument for superluminova. Let's go back and do that. All right, so with the options we selected, I said the superluminova, and for criteria 1, it glows for 15 hours, right? That was longer than any of the others that didn't use nuclear energy. And then for criteria 2, that's minimizing health impacts. If you know that nuclear energy is harmful for your health, you could just say it does not release or does not use nuclear particles in any way, shape, or form, which are harmful to one's health. On the official scoring key, they also accepted superluminova uses sunlight as an energy source. So that's it for this cluster. If you found this helpful, be sure to like the video and subscribe for more walkthroughs. And when you're ready, you can watch the next cluster review, which is going to be on chemistry beverage carbonation.